Okay, hello everybody. Today we want to talk about, so in the first session, we want to talk about the electric and the magnetic dipole moments. So the thing is that for dielectrics, which are, we're talking about non-metals, for dielectric, when they are inside an external field, what happens with them is that they react differently. So it has free electrons, and since there are some free electrons, they organize themselves in actually they're not like free electrons of the metal, sorry, but they can just rearrange. The electrons inside the dielectric, they can rearrange. Once they rearrange, they create a construct which is called a dipole, an electric dipole. An electric dipole, we've drawn it here, is composed of a plus charge and a negative charge at a distance d, which is fixed. Now, these electric dipole moments, we see them a lot in molecules. I think we mentioned this one the last time, or last week. So we said that if we have a molecule which is not it's not diatomic, such as O2, two oxygens, or H2, two hydrogens, or N2, two nitrogens. So if you have any one of these, the electron cloud, it's equal on both sides. But if one of the chemical materials, it has more electrons in its outer shell, then we have a dipole moment because the density of the electrons on one side it will be larger than on the other side. So for this case, we have a dipole moment. Now, in micro scale, we have this dipole moment, electric dipole moment. But in macro scale, this gives rise to a polarization, which is a very important parameter when we construct the relationship between the electric flux and the electric intensity, electric field intensity. Similarly, we observe the same effect in magnetic materials. For any small current that moves in a closed loop, we can find a magnetic field at some distance r from this small loop, but then this small component, which in micro scale, it corresponds to a magnetic dipole moment. In macro scale, this gives rise to the magnetization vector. Now, let's start to derive the electric dipole moment. So the construct here is that we have a positive charge and a negative charge, and we want to find the potential at some point d far away from this dipole moment. Now, the distance from the center of this dipole, we just denoted this with an r, and this is the positive charge, and this is r plus away from the point B, and this is the negative charge is r minus away from the center of the dipole to the point of interest P. So again, we are looking to find what is the potential at point P. So this is the question. And one thing that we consider here is that we assume that this dipole is so small that the distance d, this is much smaller than r, okay? So in this case, whenever we see this, any term, this means that any term that is d over r squared, so these terms are to be neglected, okay? So this is what we mean with this infinitesimally small d with respect to the r. Now, the distance of the positive charge, we denote this one as r plus, and we can write this one as r minus d half of d cosine theta. The reason is that if we can see from here, we have the following. So r minus r plus, this is equal to how much is this difference between these two quantities. And the difference is equal to this parameter. And this parameter, this is equal to half of the d times cosine theta. Because here, this triangle which we see here, this little triangle here, we have an angle of 90 degrees. This d over 2 is the hypotenuse, and it's something like this. We have a d over 2 here, we have a 90 degree here, and so this is the 90 degree angle. Hypotenuse is d over 2, and we know this angle is theta, and we're looking for this side, okay? So that's all we're looking for. Probably I can better draw this one here. So we have this d over 2 distance, and we have a direction like this. This angle is 90. This angle is theta. This is d over 2. And the question is, what is this side? This side is equal to the hypotenuse times cosine theta. Okay? So this is what we see here. So apparently this distance, and if we have two of these, okay, because this is the negative side, then this distance, these are equal. This is equal to this, is equal to this, okay? And the idea is that the distance of the positive charge is r minus d over 2 cosine theta, and the distance of the r negative here, it's a little longer with respect to the r by this distance, by this much, okay? So if we draw them again here, this will go like, sorry, this will go like this, this will go like this, and this is not the best drawing, but here we go. So this is equal to this, and with respect to this r in the middle, we can find what the r plus and r minus are. And then the potential that we're looking for is written as kq over r plus k minus q over r minus, because it's a negative charge. And we substitute here the r plus and r minus, and we get this expression. And what we can do is that we just add up these two terms together. We have the common denominator, which is here r squared minus d squared over 4 cosine theta squared. And if we add up the numerator terms, we get d cosine theta. And if we put all of these together, we said that d was much smaller than r. Okay, so d was much smaller than r. If this is the case, then the d squared, it is similarly much smaller than r squared, okay, which is completely negligible. So with terms d to the power 1, they can survive. We cannot cancel them out, right? But anything which is d squared, this can be completely taken away, and we're left with this term. Now here, we define a new quantity, which we had mentioned this one in the past week, which is that we have a dipole moment, P, which is equal to QD. Okay? So this is some new quantity, which we substitute this here. And this QD, we can write this one, okay, so here we have it. So from this part, we come here, and we write that the potential V is equal to K times the dipole moment times AR over R squared. Now this AR, we write this one in the spherical coordinate system because we want to find the potential at any point with respect to the dipole. Now for a moment, since we are assuming, so let's think for a moment. If this dipole was huge and we are looking around the dipole moment, we might have considered the cylindrical coordinate systems. But since the dipole moment is so small with respect to the distance, this is like a point. So, like a point source, which means that we could calculate, we can use the coordinates, the spherical coordinate system, because we're assuming that we want to find everywhere what is the potential. So in this case, we remind ourselves that the coordinate system pointing away from some source, this is going to be equal to AR, okay? And then this is the A theta. So at this point, this is the A theta. Probably I can erase this part here. So if this is the AR, A theta, this is orthogonal coordinate system, A theta. And A5 is the cross product of these two terms. Okay, so A5 will be equal to AR cross A theta, and we'll have the A5 going into the board. So this is why this term appears, and this cosine theta is really because of the P dot product with AR, we get the cosine theta term. Now let's think for a moment. Now the direction of P, this one thing that we don't know yet. The direction of P is AZ. Okay, the direction of P is from the negative charge to the positive charge, which means that so P, we can write this one, P is equal to PAZ, P is equal to PAZ. So if we're looking for any point around here, then we can find that the dipole moment has its maximum value, because this cosine is going to be 1, okay? But if the angle theta is pi over 2, which means that we will be looking for any point down here, because the distance here is equal, we can say that for theta equal to pi over 2, or theta equal to pi over 2, the potential is equal to 0. Okay? So it's really that if we have a dipole which looks like a pen, anywhere, or let's use this, anywhere at an angle of pi over 2 around this one, right at the center of the dipole moment, the potential will be equal to 0. So now this is what we find for the potential. Then, in order to find the electric field which is created because of this dipole moment everywhere, we can use the relationship which states that the electric field is the gradient of a potential field. Now, this gradient of the potential field, all we need to do is we need to apply the deck operator in spherical coordinate system. So we just go to the formula sheet, we look at the deck operator of the spherical coordinate system, and this is what we get. So now we have the derivative of the potential with respect to r. So here we have 1 over r squared. The derivative of r squared with r, it's minus 2 over r cubed. Okay? So this is where we have the r cubed term, and this is the 2. And the derivative of the potential with respect to angle theta. So we look at this term here. So what is the derivative of cosine theta? The derivative of cosine theta, it's minus sine. Okay? And then all the terms are the same, only that we have this extra 1 over r term. So this was 1 over r squared, plus another 1 over r, this will become 1 over r cubed. Okay? So finally, if you check carefully this expression again, we find that the electric field is equal to, sorry, this is a, no, sorry, it's not a vector anymore, but the electric field is going to be this expression. Okay? So this was the expression for the dipole, electric dipole moment. Now, a similar situation can be constructed for a current that has for a loop which has the radius b, and we have a current I that flows through this circuit. Sorry, through this piece of wire. So if we have this current flowing over this piece of wire, we can try to identify the. Let's draw first the coordinate system. So this could be our x. This would be our y coordinate system, and this would be the z. And we are interested to find what is the magnetic field at some point p at a distance. So we have to draw, so this point p with respect to the coordinate system, which will be centered at the center of this closed wire in the form of a circle. This point p in the spherical coordinate system will have a distance r. Okay. So, and then here we can have an angle theta with respect to the z-axis, and we know that the projection of this point down here, we can find it by knowing what is the angle phi. Okay. So this is how. So this point p, this is at any distance r at any angle theta with respect to the z-axis, so we are dealing with spherical coordinate system, and at any angle phi. Okay, so this is the coordinate of point P, and the thing is that in order to find the magnetic field, we assume we get an infinitesimal small current element. So this infinitesimally small current element, it's something which is allocated somewhere along the wire. So let's assume that this is along the wire. And we need to identify what is DL, okay? So this is the question. The first thing, when we apply the Biot-Savart law, which is a mathematical construct which was formulated by two French physicists and mathematicians, they constructed this law for which we need to know the DL term and 1 over R term. Okay? I'll clarify this one in a moment what these are, but this 1 over R is not the distance of the center of the loop that carries the current, but is the distance of this element, of this current element. So it's going to be this other term. Okay? So this will be, let's call this one R1. Okay? Now, let's see why we need these. Let me take out this part on the board. Okay, we can preserve this one. So in order to find the magnetic field from a source, we need to use the Biot-Savart law, which states the following. It states that we can find the magnetic field potential. So we can define the magnetic field potential A, which is going to be equal to mu0 I over 4 pi times the closed line integral over of dl prime over R1 in this case. Okay? So this is the magnetic field potential A. Now, let's leave this over for a moment, the result for the electric dipole that we found before a while. And then when you look at this expression, it looks like pretty trivial because these are constants, so this depends on the current, and this is dl over R1. So that's it we need to know. Okay, so we write this one in the formula sheet, and then we run after to find out what is dl. Now, dl in this coordinate system, it is defined as the length of this arc. Okay, so since this is an arc, so what is the length of this one? Okay, so since this is an infinitesimally long element, we can determine. We can write this one as R d phi, okay, where phi is the angle in the xy plane, okay. So this is the angle phi, but since this is, and this R is B, is a constant, so this is going to be B phi. Are we missing anything? Probably, but let's assume this is, we need also the direction of this DL, and the direction of this DL is A phi, okay? So it's going to point in the direction, so A phi is always tangent to this closed loop. So, okay, that's it. We found the DL term. We can substitute it over there, and we should not forget that this is a vector notation. And then, this is the first part, and the second part is to find the R1. Now, in order to find the R1, what we see here is that this is approximately an angle which is by 90 degrees. And the R1 is going to be an expression which we can find it using a couple of approximations. And so it's going to be, so this R1, this is going to be R1 as a function of R, the distance R, and the B. Okay? And the general idea is that this R is going to be, let's see, the approximations. We can skip a small part of these, but we might skip just the part where we derive the complete expression for R1. It is similar to what we did for the electric dipole, and here 1 over R1. This can be expressed as 1 over R times 1 plus B over R sine theta sine phi. Okay, and we write this one sine phi prime because with prime we denote the quantities where the sources are. So the source is a current, so that's why we denote those with phi prime. And now it looks like we know DL, we know this quantity. We know also this 1 over R term. So if we include these into this expression, and we can also observe that we can observe that we can, so this 1 over r, we can multiply both sides with b. Let me think for a moment. So this is 1 over r. We can multiply with dl, and the dl is what we wrote here. This is b d phi. In fact, this b a phi times d phi. Let's write the d phi here, and then we need to integrate. This is 1 over r. Let me write the b here. So this is a phi b over r times all of these terms. So, and this, we take the integral from 0 to 2 pi, because these are the limits of the phi. So if we apply if we integrate this expression, we find that the vector A, the magnetic potential A, this is equal to a phi times mu I d squared over 4 pi 4r squared. This is 4 over 4r squared times sine theta. Now, and this, we can also do a recollection of some terms. And for this, we can write this, this whole thing as mu 0 m mu 0 m cross product with AR. Cross product with AR. And over over 4r squared. Okay, so this is the magnetic field potential. The same way that the scalar potential is the source for the electric field, here the source for the magnetic field is going to be this term. Now, the reason I kept this one here on the board, it was because we can observe a similarity between the, and by the way, I think this phi, it is here. We have again this phi here. So we can observe a similarity between this potential and this potential. Okay? So scalar potential and the vector potential. Now, having this, the next step that we can do is to find the magnetic field, the magnetic field B, the relationship with the vector field A is equal to the cross product of the with the del operator. So this is going to be the B. And if we apply this this operator, what we find is that the B, the magnetic field, which is caused by a current which moves in a closed loop with a radius b at any distance r, this can be given as mu 0 m. And I've not said yet actually what is the m, the small m that we define. Apparently it's a vector quantity, and we'll make it clear just in a moment. But here we have mu 0 m over 4 pi r cubed, and here we have AR, we have a component along the AR direction, 2 cosine theta plus A theta plus A theta times sine theta. Okay, so this is the magnetic field vector. Now, what we need to make clear here is we need to define what is the magnetic moment M. This magnetic moment M, this is a vector which is the direction of AZ. We call this AZ because if the current is flowing across in this loop, in this direction, we use the right-hand rule, and if the current is flowing in the direction of our fingers, it's like defining the vector for a surface area. We know that the surface area is defined uniquely by a vector which is perpendicular to the surface area. Okay? So the same way we do here. So this moment M is equal to AZ times I pi b squared. Okay? So this is I pi b squared, which so So it looks like the magnetic moment, it has absorbed inside the current and this expression, okay? So we have the current and this expression, so we get this. So it looks like the magnetic moment m, this small m, this has units of amps, ampere, the unit of current, times meter squared. Okay, so these are the units of this magnetic moment, and this is small m. Now, what we can do is that we can summarize these terms, and probably I can give me a second. And I'm going to rewrite this again, but this k is 1 over 4 pi epsilon 0. Okay? This constant here. And but let's put them in the same formula, including their similarities. So we saw how they look like, but let's write now what is the potential V, the scalar potential V. This is equal to 1 over 4 pi r squared times 1 over epsilon 0 dipole moment dot product with AR. Okay, so this is the scalar potential for the electric field, and the A is equal to 1 over 4 pi r squared times mu 0 times m cross AR times m cross AR. Okay, so the expressions that look very similar with respect to each other, only the 1 over epsilon 0 is substituted with 1 over with mu 0. So 1 over the permittivity, it is substituted with only the permeability. And now the electric field, which is found from the source, from the potential source, this is equal to P over 4 pi r cubed 1 over epsilon 0 times, here we have AR AR 2% theta, this is AR 2% theta plus A theta plus A theta sine theta. So this is the expression for the electric field. Now for the magnetic field, this is going to be, so if we compare this expression with this expression, the only thing that changed was, for example, if this is P, we can write here the magnetization, the magnetic dipole moment. So we just change the P into the M, 4 pi r cubed. 1 over epsilon 0, probably this should be enough, okay? So these are only the distinct differences between the magnetic field and the electric field. And the rest will be the same, okay? So this is going to be, again, AR 2 cosine theta plus A theta sine theta. So let's try to clear this a little bit. So what do we notice in these expressions? So it looks like we can, let's have a look. Let's find a different color. So we have only these specific terms are different and this term here. And everything is the same from for these infinitesimally small sources. And these are the sources of the respective fields. And now another thing that we observe is which are very important is that the potential from a dipole as a function of the distance it's changing as 1 over r squared. So if you have just a point charge it has, so if you have point charge here, and we have to find the potential far away. We know that the expression for the potential is kq over r, okay? So the potential is proportional to 1 over r. But here, we did a couple of approximations, and as a result, we find the potential is proportional to 1 over r squared, and similarly, this term is also proportional to 1 over r squared. Now, since the electric field is a space derivative of this potential with respect to r, that's why we get here r cubed, okay? And similarly, since the A itself, now this A, this is a vector, this in principle is proportional to 1 over r, okay? But since we're doing some approximations, because, and again here, the B, the radius of the loop, is much smaller than r, okay? So we follow a similar approximation that we use in the electric dipole moment, where the D, the distance between the two charges, it was much smaller than r, okay? So now, for these reasons, the A, which is traditionally proportional to 1 over r, it's here 1 over r squared, and since the B is a space derivative of A, that's why we see here it's 1 over r cubed. Now, having the derivations of the electric dipole moment and the magnetic dipole moment, having them in one piece of sheet or on the same board, we can also figure out their similarities and their respective differences. So let's clear this out, and let's have a final look here. Now, so during this work, we defined this little p, which was the dipole moment, and the density of these small dipole moments. This gives rise to a polarization, which is the representation of this quantity in microscale. This is the representation in macro scale. And now we have also this small m, and this small magnetic field dipole. This gives rise to the macro scale, which can be observed at a huge piece of metal or piece of conductor, which is called the magnetization. Now, this polarization and the magnetization, we find these expressions when we write down, so the electric field flux. This is a relation, it depends on the electric field and on the polarization. And similarly here, we have the magnetic field flux, so these are fluxes. These are also expressions of magnetic field intensities and magnetization vectors, okay? So this is what we're going to observe pretty soon. So again, microscale effects, and these are macroscale effects. So we keep this this much at this part.